My name is Daniel Feltham. I work at the Centre for Polar Observation Modelling in the Department of Meteorology in University of Reading. So my area is climate process physics.
My name is Alexander Korobkin. I'm from University of Anglia in Norwich, School of Mathematics. I'm a applied mathematician working on mathematical models of ice in particular.
I'm Vernon Squire. I'm actually from New Zealand. I work at the University of Otago, which is in Dunedin in the South Island. And my particular interest is in the way ocean waves and sea ice interact.
My name is Emilian Parau and I'm working at the School of Mathematics at the University of East Anglia. I'm an applied mathematician working on nonlinear water waves, hydroelastic waves and other fluid mechanics related problems.
Our program, scientific program, sea ice, mathematical sea ice phenomenon, is about mathematics and about sea ice and models, how to model sea ice, how to construct new models and how to develop further the existing or classical models. And it's very challenging because the ice is a very unusual material on the Earth. It's very different from anything existing. So it's depending on situation, depending on the even place. It behaves differently, and also it's affected by many things like ocean, atmosphere, current, waves, ships, people, everything working on it, and so it's about modeling of and prediction of ice behavior in different conditions.
And I think it's worth also mentioning that we are talking about sea ice primarily. Sea ice is frozen seawater as opposed to icebergs, which are pieces of ice that have essentially broken off land ice. The main focus of the program is sea ice, although we do have other kinds of ice there. So we do have experts from other areas of ice physics and ice mathematics. And river ice is also important. Yes. Yesterday we had a lecture all about river ice, and river ice is very crucial when you've got a hydroelectric power station or something and you get these blockages of the river due to ice jams.
Or I think of aircrafts also included in our program. I think of ships and I think of aircraft, so that would be many.
Yeah. So there's a broad range of length and timescales involved in the sort of models we're developing. So at one end we have people interested in climate models, at the other end we have people interested in really like small scale, centimetre scale models of sea ice. So the challenge is to get the unifying features across these models and the possibility to prioritise which properties of which things need to be modelled accurately to get realistic representations at the appropriate length and timescales.
And I think one of the strengths of the program is that there is a mix of polar scientists, mathematicians, engineers, so it's a very large array of disciplines which are covered by this program.
Yeah. Good mixture of everybody.
Well, we're mostly interested in ice forming in its natural environment, and what makes us particularly timely of this is the rapid reduction of Arctic sea ice. Over the last 4 decades, the summer extent of Arctic sea ice has halved in extent, and there's been a accompanying decrease in volume. So this dramatic reduction in the Arctic ice cover, and in particular why there isn't a reduction in the Southern Ocean sea ice cover, by the way, is of great interest to climate modellers, and also has huge impacts to those who work and live in the Arctic. So the rapid change in the sea ice cover is energising people's interest in understanding the mechanisms of the reduction of the sea ice cover. And so that's what's driving a lot of, certainly from the climate side, a lot of the interest in the fundamental mechanisms of ice reduction. And the reduction in the ice cover is opening opportunities to the Arctic as well, so navigation across the Arctic, oil exploration, and this has attendant challenges, engineering challenges. So that brings extra interest as well.
And one of the foci of the meeting has been trying to understand the role that sea ice actually plays in these large-scale climate models. And also the reasons behind, as Danny says, the reasons behind why the sea ice is disappearing in the Arctic, but it's not disappearing in the Antarctic so nearly as fast. In fact, in the last year or so, it's expanded in the Antarctic. The large-scale models are actually very sophisticated now, and there's significant recognition that sea ice is very important. We don't fully understand, as I said earlier, why the sea ice is vanishing, but we're recognising that it's a mixture of many processes, and the conference, the workshops are very much about trying to understand how those processes interact with one another. For example, we know that the reflectance, the albedo of the Arctic ice has changed quite significantly. There's a lot more meltwater on the surface, which makes it much darker. We also know that because there's less ice, there are much larger waves in the Arctic, particularly, than there used to be 20 or 30 years ago. And those are particular interests of the group that's meeting at the moment, actually, in the workshop that's currently taking place.
So Daniel mentioned the resources of near North Pole are important, and kind of the several countries are trying to get there. So we have to find to get there. Then the ice is getting smaller in north, and so the so-called north route is getting open. So the ships can go from Atlantic to Pacific Ocean much quicker. This means more money can be get from it. So it's economics as well. It's not just climate change, but it's also economics. But the ice is still there. So there is the floating ice. So the ships should go from that ice, and they could be a very complicated situation when can be trapped in ice. Even they do not expect it. So we need to know this, and we need to fight with them. And, also, yeah, mathematically, it's getting we arrive at that stage when, yeah.
Yeah, I think it's timely also because the computers now are more powerful.
Yeah.
And finally, we can hope that to include this effect of the sea ice on the atmospheric or oceanographic global models.
So it's very timely program from many aspects.
Another example of the economic aspects of what we're looking at is certainly in New Zealand, and I presume in the UK and in other countries, there is a TV program called Ice Road Truckers, and the basic idea of this is, and it's actually taking place every year, that when the cold weather comes in, say, northern Canada or northern states, there's an economic advantage for vehicles to travel over frozen lakes. And one of the focuses that we've seen in the last few days has been trying to work out what happens when a moving load travels over ice, and it deflects the ice downwards, and of course the trucks can break through, but generally they don't. The ice deflects downwards, and the amount of deflection depends on the speed at which the truck is travelling. So if we can actually work out the ideal speeds for the trucks to travel at, we can avoid major accidents, and also, as I said earlier, there are massive savings involved because the distance across the lakes is much shorter than the distance around the lakes. And so some of the mines in northern Canada regularly every year use these transits over frozen lakes and permafrost.
So the challenges of modelling that sort of phenomena can be quite different from the challenges of modelling sea ice in the climate system, plus sea ice prediction for navigation across the Arctic. So this whole host of challenges bring up different facets of the problem. So people approach the problem in different directions, and they focus on different areas, which is great and interesting, but we also want to bring people together to identify the commonalities.
Yeah.
One of the main issues of sea ice particularly is that naturally it grows in a variety of forms. The structure of sea ice depends very much on the speed at which it grows. It has a temperature difference between the top and the bottom. The top's at air temperature, the bottom's at seawater temperature, which is about -2. It is very heterogeneous, it's very non-uniform in terms of both space and time. So if you walk across sea ice, you're very likely to encounter different types of sea ice. And then structurally it's very different on all scales. So again, if you walk across sea ice, you'll encounter ridges, which are sort of little mountains in ice, which have keels underneath, and those keels can stretch down sometimes as much as 40 metres under a 1 or 2 metre thick ice. So the material is incredibly diverse in terms of its properties, and that makes it very hard to model. And so that's one of the major challenges. Another major challenge, in fact, which I think makes the field very exciting, is bringing together the experimentalists and the modellers and making them see a common vision for where the subject is going. The modellers tend to be, of course, too perfect in the way they think about things. You know, the old take one spherical cow model. The experimentalists are very quick to bring the modellers back to reality. And what we need is a sort of central path where we're pragmatic enough to realise that we can't represent all kinds of sea ice in all its forms, but we still need to move the subject forward.
Sea ice cover is, as Vernon said, hugely spatially heterogeneous and across length and time scales. And this means that people working on one particular parameter regime, one space and time scale, can develop quite idealised, almost exact models of their particular process, which is great, and that's interesting. But when one's trying to look at the evolution of the ice cover as a whole, which one might be interested in for weather models or for climate models, bringing all these idealised, good understanding of a particular process into one model can lead to emergent complexity, which is not the sum of its parts. Okay? And so one of the challenges is finding which are the important things to include into these models. Somebody who spends 20 years working on one aspect of the ice cover, it may be unpleasant to them to find out that their aspect of physics has a relatively small impact on the emergent behaviour. So it not only is it getting a detailed understanding of processes, but the emergent interactions between them. And that's quite a big challenge, especially of climate modelling.
One of the challenges is, for example, the interaction of the waves with the marginal ice zone, when waves go from the free ocean to the solid ice. And there are a lot of interest in understand the attenuation of these waves on this area. And that's one of the main topics of this workshop this week, for example.
Very big mathematical challenge that working with uncertainties. So we now, as my colleague said, we know almost nothing about ice. I mean, okay, we can investigate it, but once we just arrive to the place, we know nothing. So it can be anything. So, and still we need to do something. So, okay, it's not a unique problem. The many processes in our life, they are uncertain. We do not know condition. We do not know what's behind it. But that is the kind of the challenging and everything at one. And so many things, and Daniel said each effect on its own could be important or not, but once they combine, once they work together in combination, the effect could be different. They can work in different ways, so this is amazing. So it's a so rich variety of the processes, of the interaction of everything. It's a very challenging and exciting field of research and practical field as well.
I think it's also worth saying that, I mean, it is a very exciting field, but one aspect of it that does make it very difficult is that it's not simple to actually collect data. You know, we're talking about a material that grows at temperatures below -2, let's say, down to -40. And so the conditions under which these experiments take place make them very difficult to do. And the meteorology, the local meteorology, can be unbelievably bad. So one can go out to do an experiment which might be relatively straightforward to do in the lab and never succeed. You may sit in a tent for a week. You may never even arrive in Antarctica because the air conditions, the weather conditions are too bad and your flights are turned around. So we have to factor all that in. That makes the dynamics between the mathematicians and the experimentalists very interesting.
Well, it also brings up the utility of laboratory analogues.
Yeah, absolutely.
Absolutely.
Yeah.
Well, sea ice research is interdisciplinary, bringing in experimentalists, laboratory experimentalists, field scientists, physicists, mathematicians, biogeochemists, in fact. So we bring a lot of science from disparate areas into discipline. There are also some areas where sea ice is a good way to explore new physical processes. So one observation is that sea ice is pretty much a binary alloy of salt and pure water, close to its freezing temperature, and so that makes it a fairly unique material. So morphological instabilities in these binary alloy systems can lead to what are called brine channels or brine tubes in the ice cover. Now, these are also common in alloy systems such as steel. So the brine tubes which transport salt from the sea ice into the ocean are very important for modelling the ice and ocean systems. Also, other things you want to avoid when you make metal casts. So observations and experiments on sea ice also gives rise to insights which feed back into metallurgy and other areas. Another example is in fracture mechanics and frictional sliding. So, I mean, widely different length and time scales, but thin plates of sea ice sliding past each other have frictional forces there, and they can freeze together and rupture. There are similarities with plate tectonics. So for example, I've been involved in ice tank experiments looking at stick slip, which is when you have sliding, it sticks a bit and it slips again. Okay, and that is directly pertinent to plate tectonics, but that's something which we can measure and analyse much more conveniently for sea ice than we can for plate tectonics.
Still in mathematics, there is some impact of direct or not direct impact of our program. It's, as we discussed, dealing with uncertainties. That is the important, and not just dealing, but understanding what this is for. Because if we study ice models from point of view of kind of orthodox or classical mathematics, we can find that the models are not really good. So they're very sensitive to conditions, they're very sensitive to parameters involved. But on the other hand, the understanding properly, and that is understanding and how to use the model, is come together with the mathematical model. That is the important part, and that is, should be specified and explained. And that is important not only for CIs, but for many other processes, when we do not know the conditions or parameters exactly. And as we discussed, there are many such processes. And we can also working in this field. As to me, from mathematical point of view, I see that there is already big progress, and we did a workshop on hydroelasticity in 2011 and discussed with Vernon and Emilian what to do next and other. Now we are about doing this. Okay, they're still discussing, but there are already a lot of things done from 2011. And, it was workshop in Edinburgh, the Centre of Mathematical Sciences. And so, like that time, 6 years ago, the nonlinear process is just kind of started. But now, today we had a session. Today or tomorrow, yesterday. Yesterday we had a session on nonlinear processes in ICE. So next it would be, okay, we discuss again, it's nonlinearity and dissipation, how to combine them. And many other things. So the experiments, field, the observation, everything gives the ideas for mathematical modeling, the development, and hopefully benefit to ICE people who are actually working with ICE every day or main part of the year.
And one of the things that's happened over the last 10 or 20 years has been the development of very high precision in the sense of knowing exactly where they are, satellites. So we know there's a lot of satellites now that are environmentally sensing the Earth in various ways. So they often have active radar aboard or passive radar. They can measure the wind at the sea surface. They can do all sorts of things from space, and there's several satellites up there at any one time. Now that's allowed the sea ice community to have a wonderful instrument that allows us to look at what is essentially a non-Newtonian fluid on the surface of the Earth, and by creating theoretical constitutive relations to represent that rheology, we're taking the subject of non-Newtonian fluids forward, while also having very, very good measurements from space of how that material behaves on a large scale.
Yeah, I think it's worth saying that's completely transformed the subject of sea ice dynamics. So maybe 10 years ago, or maybe 15 years ago, we could measure the extent of the sea ice cover, so its horizontal extent, but we didn't actually know how thick it was. So various different models could predict the extent with some accuracy, but they could have widely different sea ice thicknesses. So until you have this data, you can't constrain in a meaningful way the momentum balance, the rheological assumptions in your models. This has really re-energized the subject of sea ice dynamics. So there's a lot of work going into how to best characterize the sea ice stresses in the ice cover now.
I was also absolutely flabbergasted just a year or so ago when I read a paper which was, again, going back to this moving loads on sea ice trucks going over sea ice, where the satellite was actually the satellite was able to see the wake created by a truck moving over a lake from space. The way that was done is interferometry, so essentially two instruments and measuring the phase between them. But to see a wake from space, that is the waves that are created by the truck in the ice surface, is just amazing. It just demonstrates the resolution that we're capable of actually achieving.
And you're talking about something of like 1 to 2 centimeters.
1 or 2 centimeters, that's what we're seeing from space, from 800 kilometers up. I mean, it's just the interaction with that.
More and more, better and better equipped to develop better models, mathematical models.
That's right.
In particular,
well, technology has massively influenced the subject in all ways.
Everything.
Even in some mathematics, there is a lot of collaboration at this conference between pure mathematicians and applied mathematicians, and people proving theorems or people doing modeling. So I think it's quite a good dynamic.
It could be not directly, but it's